Question 8, everybody's favourite, the motor effect. Okay, the motor effect. It's the one that I know that when I teach it, it's the one that students always find the most difficult. My advice to you now is, if you don't yet understand the motor effect or be able to explain it well and you're not confident with it, is you've just got to learn it rote at this point before the exam, because it's always asked in a similar way. You are explaining an effect, and it's consistent, and it's always asked this way in an exam paper, and you've just got to write down the points. So that's how I'm going to answer it. I'm going to use bullet points. This question's worth 4 marks, and we're just going to try and hit those 4 marks. So we need to explain why the wire moves. And that's the whole thing. That is the motor effect. So basically, some electricity is going to flow through this wire. All right, the wire is in a magnetic field, and when the wire is in a magnetic field and you've got a current flowing through the wire will move. And you can use Fleming's left-hand rule in order to figure out which way the wire will move, but that's not what this question is about. So we just need to do the very basic explanation of what happened. So we're going to start out from having a look at the diagram, and in this case we've got a switch. Now a switch is all about opening and closing the circuit. So if we close the switch, we close the circuit, and therefore the current can start to flow. So that's the first thing we're going to say, and we're just going to go so when the switch is closed, a current will flow through the wires. Okay, so the current is now flowing through the wires. So it flows conventional, positives, negatives. The current is going this way around the circuit. As you can see, it goes down through where that where the wire is in the magnetic field. So what will happen here is that when we've got a current flowing through a wire, one of the things that hopefully you've learned is that a magnetic field develops around the wire, and now that magnetic field is circular, so you get this circular magnetic field, and you can use the right thumb rule if you want to figure out the direction of that, but we've got a magnetic field around the wire. So we can say, so when the switch is closed, a current flows through the wire. The wire has a magnetic field induced around it. Induced means made. So that the fact that the current is flowing means that a magnetic field is produced around it. So when that magnetic field is inside that magnet, and you'll have seen this, it's a dead simple idea. If you put 2 magnets together, you should hopefully know that they'll either attract each other or they'll repel each other. But either way, the magnets will move. So if you bring 2 magnets together, they will move. And that's all that's happening here, is because the wire is now a magnet. We've got this magnetic field around it, and it's been placed inside a magnet. So in this area here, inside that magnet, that wire will move. So that's what we're going to say. So let me grab the pen. And so the magnetic field of the wire interacts with the magnetic field of the magnet. So when the switch is closed, current flows through it, the wire gets a magnetic field. The area where the wire is passing through the magnetic field of the wire interacts with the magnetic field of the magnet, and we know that if two magnets are pushing each other, they move. So this causes a force to act on the wire and it will move. Just like when you bring two magnets together, they move because there's a force, either a force of attraction or a force of repulsion. Okay, that is that. And as I say, I would just practice learning those 4 bullet points. And it's always going to be something like that. You know, you close the switch, that causes current to flow. The current causes a magnetic field to produce around around the wire. When you place the wire in a permanent magnet, those two magnetic fields interact. That causes a force on the wire. The permanent magnet can't move, so the wire moves. That's why. Okay, part B. Part B, it says the student recorded these measurements and they had the potential difference across the wire of 1.5 volts. So this looks like we're going back to a formula question. Fortunately, we have to go to the next page. We've got the resistance of 0.6. We have got a length in 0.05 meters. And we've got a force on the wire of 3.75 times 10 to the minus 4 newtons. And it wants us to calculate magnetic flux density. So, luckily, there are not many equations that have magnetic flux density on them. So what we're going to have to do is we're going to have to go to our data sheet and we're going to have to find the formula for magnetic flux density. So, I'm just going to get rid of all the stuff we previously had. Okay, so you can see that I looked it up earlier, but I've got it on here. So I found it here, look, magnetic flux density. It's the only formula that's got magnetic flux density in it. So magnetic flux density, so we use this formula, F equals Bill. So force on a conductor is equal to magnetic flux density times current times length. So we're just going to write that in, F equals Bill. So in our formula, so we'll use FIFA again, so the formula equals F. So the force is equal, I'm going to give this plenty of space because I can see that this force here, all right, is actually quite a big number. So force equals B, magnetic flux density, times I, that's the current, times by L, which is the length of the wire. Now I've been careful to use the same casing as shown on my formula sheet. So I've not got an uppercase L, I've got a lowercase there. Capital F, capital B, capital I, lowercase l. So I'm going to input my data and let's see which of these I need. So the force, now I've given the force here, it's 3.75 times 10 to the minus 4 is equal to magnetic flux density, B, which we don't know, so we're going to leave it as B, times by current. Okay, we have not been given a current. We've got a potential difference, resistance, a length, and a force. We don't know a current. Times by the length of the wire. The length of the wire is 0.050. And it's in meters, so that is the correct unit. So, got a bit of a problem because there are two unknowns. I've got an unknown B and I've got an unknown I. It wants us to find the magnetic flux density, so I'm going to have to somehow find I before I can do that. Now, the way we do this is what we call a link equation. And on a link equation, it means that you have to use another formula in order to find a missing value in this formula. And I'm going to work out my link equation in this top area here. So I'll do it in red, so I'll do it in blue, just so that it makes it obvious to you which is the different formula, because otherwise this could end up looking a bit complicated. So we have to think about what we've got. We want a current, all right? So we're trying to find the current. So we can think about what we've got. We've got resistance, we've got length, we've got force, and we have got potential difference. I'm just going to write these here. So I've got a potential difference, I've got a resistance, I've got a length, and I've got a force. So I'm looking for something that can have current with any of these two values, because they're the ones I know. So let's go to our data sheet and grab the highlighter. So I'm just looking for the word current. Okay, I am not seeing the word current on that page. Let's move to the next page. So the front of the sheet, looking for the word current again, for the word current. I found the word current there. Charge flow equals current times time. I don't have a charge flow and I don't have a time, so that one's not going to work for us. Let's get rid of that. What about the one below it? Current, resistance, potential difference. V equals IR. I do have those things, so I'm going to use V equals IR. So, my linked equation. I said I'm going to do it in blue. Phi for V, the formula equals I times by R. The potential difference I do know. It was given here, 1.50. So input these values. 1.50 is equal to the current, which I don't know, but I am trying to find, times by my resistance, which I do know, which is here, which is 0.60. So I can solve this for I because I've got all of the other values. So that's what I'm going to do. So I'm going to have to fine tune it in order to make I the subject. So what's happening to I? Well, it's currently being times by 0.60. So I'm going to divide by 0.60. And that will cancel out, leaving I on its own. But if I divide that side of the equal sign, I have to do the same to the other. So 0.60. 1.50 divided by 0.60 is equal to I. So I'm going to write out that 1.50 divided by 0.60 is equal to I. So let's figure out what I is using this calculator. Okay, get rid of that stuff. There. So 1.50 divided by, I like to use the fraction function, 0.60 gives me 2.5. So I equals 2.5 and it will be amps because that's the current. So now I do have a current value. So I'm going to go back to my first formula and I'm going to write it in, but I'm going to replace the I now with that 2.5. So my full input is 3.75 times 10 to the minus 4 is equal to B times by 2.5, because that's our current value, times by 0.050. And I'm now at a point where I can solve this because I've got only one unknown value there, which is B. So I'm going to do the same thing. I'm going to do the inverse of what's happening. So I'm going to fine tune it. So we're going to end up with doing this. So B is currently being times by 2.5 and by 0.050. So we're going to do the opposite. We're going to divide by 2.5 times by 0.050. I'm going to put that in a bracket because that's one function. And if we do that, that will cancel that because we've got the same times by and divide by, so opposite functions, which is going to cancel out and leave B. But we've got to do the same on this side. So 2.5 times by 0.050. And let's write out our formula as it now stands when it's been fine-tuned. So 3.75 times 10 to the minus 4 divided by, I use the fraction function, 2.5 times by 0.050. That is our formula, and if we do that, it will give us B. So let's see what answer we get. Now, I have done this before, and the calculator that I use on my iPad isn't the best for this type. All right, you're much better with your standard scientific Casio, but let's give it a go. So 3.75 times 10 to the minus 4. Now I'm going to have to use the equals here, and I'm going to have to use the answer, and I'm going to divide that whole thing. So I'll go back. So my answer divided by, and I'm going to have to use a bracket, 2.5 times 0.050, close the bracket, gives me 0.003. So I'm just going to write that in. 0.003 is my answer. And the units of magnetic flux density are Tesla, capital T. Okay, so let's just check what we've done. So first of all, let's just check this this equation here. So 1.5, and I like to do it the other way around now. That's why I use the fraction function, so I can do it both ways. Divided by 0.60 gives me 2.5. So yes, that part is correct. So I'm happy with that. I've got my page loaded a bit weird here. Just get rid of the calculator for a second, and I want to use a split rather than whatever I've just done. So yeah, that part is correct, which means that this substitution is correct here. Okay, I rearranged it by dividing both sides by 2.5 times 10 to the 2.5 times 10. No, I didn't. Divided by 2.5 times 0.050. And I ended up with 3.75 times 10 to the minus 4 divided by 2.5 times by 0.050. So let me just do that again. So 3.75. And I have to use this exponential button here, which is a bit annoying, but it's the same thing as the times 10x button on your calculator. Times 10 to the minus 4 gives me that. I have to press equals, and then I have to use the answer, which is that. And I divided that, I'm going to use the divide function now, and by 2.5 times by 0.050, close the brackets, and I ended up with 0.003, and I've got that twice now, so I'm pretty confident in that answer. So I'm going to put those answers into here, 0.003, and the unit is T for Tesla. Okay.